Welcome back, my dear students. As we are studying the first module, in that already we have studied the Pascal law. We have proved that intensity of pressure is same in all the directions in the static fluid. That is Px is equal to Py is equal to Pz. And another one very important law, it is coming, that is called as the hydrostatic law. Hydrostatic law, what it tells here now, if this is the surface of the fluid here, if any that object or a point, it is at the bottom of this static fluid, this is the static fluid here, static fluid means fluid is not moving here. If this is the object or a small element having the height of this one is here now, the delta z here, delta z is the small height here, and this is from the surface, this is the surface here, from the surface it is having the distance here, the z here. So vertically downward direction is taken as the z direction here in this case. So what is this hydrostatic law it is telling here now? If we are moving towards the downward from the surface, here now, point is here, point is here, point is like that. If you are moving down here, like if this is the static fluid from this surface, here now, in this fluid from this surface, if you are moving down and down, how that intensity or change of pressure, and it depends on what it is telling here. So we will prove it. So then we will see how that when we are moving down in a static fluid from the free surface, how it depends on what parameter we will see by the derivation here now. So next what I will take is a small element, it is taken here now, small element of small area, this is a delta A here now, surface area here, this surface area is this one, and the height is here now, delta Z it is taken from the free surface, it is Z here now, positive Z direction, it is in the downward, it is taken here now. So in this surface here, at the top surface that the pressure, top surface that the pressure is, here pressure force is P into delta area. It is a pressure force, pressure Newton per meter square into meter square, so it will become the pressure force on the top surface. And at the bottom surface here, and at this bottom surface, it will be taken by the Taylor series of expansion here now, that is P into delta area plus the differentiation of P into delta area here, P into delta area with respect to what? With respect to the Z direction here now, with respect to Z direction, into how much that the pressure has to be differentiated here now, into it is delta Z here now. This is what? This is the pressure at the bottom surface by the Taylor series of expansion. Higher order differential equations are neglected here now. So next one, another one force is there, that is the weight of this body here now. Weight of the body. That weight of the body is it is now weight of the body is what? So therefore weight of the body, it is acting at the CG here now, rho into G here now, kg per meter cube into this is the meter per second here now. So meter cube here, so into that volume has to be multiplied here, that is delta area into delta Z, it is the volume of the small element here now. So now because this the body, this point is under equilibrium here now, so now I will take this force here. So it is all these three forces I am taking, P into delta area here minus here this total this force here now, P into delta area minus dou P into dou P divided by dou Z into this one, it is delta area into delta Z here, delta Z here now, then this one here now, because this is moving downward in a Z direction, it is taken as a downward direction, is a positive direction, so therefore plus here now, it is a rho G here into delta area into it is a delta Z here now. This is equal to 0. So this positive P into delta area, negative P into delta area, it will get cancelled here now. So next one, here in this case, this delta area into delta area into delta Z will also get cancelled here now. So next, this minus dou P by dou Z, if I take that side, what I am getting here now, dou P divided by dou Z is equal to rho into G here now. This is the equation what we are getting at the end of this hydrostatic derivation here now. What it is telling here now? Dou P divided by dou Z means what? Change of pressure along the change of the direction, Z direction here now. It is Z direction, downward direction. This is Z direction. So therefore, the change of the pressure in the downward direction at a particular point in a static fluid is equal to what? Rho into G. Rho into G is what? It is the specific weight here now, W. It is a specific weight, or it is also called the weight density here now. So therefore, the pressure is changing in the downward direction in a static fluid at a particular point. It is always is equal to the specific weight of that fluid, or else that is a weight density of that fluid. This equation is very important, that equation for the measurement of the pressure applications, especially in case of the manometers here now. How it is very important, this one we will see here. This is now, it is dou P divided by, it is a dou Z is equal to rho G here now, or else it is a weight density here now, weight density. Now what I will do this one now, so dou P I will keep here now, this is equal to rho G, this dou Z I will take in this here. Now I will integrate it here. If I integrate here now, this is the integration of dou P is P here, this is equal to rho G R constant here, because rho is the density of the fluid, its a property is a constant, and G is the acceleration due to gravity, and the dz it is having this one, Z. Integration of dou Z is the Z here. So now Z is what? Z is the distance from the free surface, where that point it is there, as we have taken in the diagram itself. So in case of the diagram, where the point it is there, this is the distance, it is a Z here now. So that is, distance is nothing but it is the height with which that point is present from the free surface here now. So sometimes this height will be represented as a h here now. In place of the Z, we can write in place of the h here now. So therefore, then next P is equal to rho GH or rho GZ here now. So this is the very important relation what we are getting here now. P is equal to rho GH or rho GZ here now, where the static pressure at any point is equal to rho G, means weight density or specific weight, into the height from the free surface where it is there, that is the H value or a Z value. So a very important relation what it is derived here now, P is equal to rho GH. This is the equation we received from this hydrostatic law. Actually hydrostatic law, what it is telling here now, the change of intensity of pressure in a vertical downward direction in a static fluid is always is equal to the weight density or specific weight of the fluid at that point here. That is called as the hydrostatic law. This is the proof of the hydrostatic law here. So now, this is about hydrostatic law. In the next video lectures, we will see the application of this hydrostatic law in terms of manometers here. Now, thank you very much.